Quadric surfaces. These are surfaces like ellipsoids, paraboloids, or hyperboloids, among others. So let's just draw a little ellipsoid here, just for fun. A little smushed sphere there. Paraboloid looks kind of like a bowl. A hyperboloid might look like this, or it might look like this. You can have other shapes as well. Let's start with a basic example to see what kind of techniques are useful. Here's the graph of the function z equals x squared plus y squared. It's a bowl, looks like this. Let's draw a couple of points on it. Here's the point 1, 1, 1 squared plus 1 squared. Here's the point 1 minus 1, 1 squared plus minus 1 squared. Now let's use maple to graph this. We'll see it looks a little different just because the way I've done it in maple here, I'll take x from minus 2, y from minus 2 to 2. So you're looking at the plot of the function over a square. So let's try to understand this graph in just a little bit more detail. It can be really useful to intersect a surface with a plane. Let's intersect it with a horizontal plane. So a horizontal plane has the equation z equals k. The surface, of course, has equation z equals x squared plus y squared. Intersect those two, you get the equation k equals x squared plus y squared, or a circle of radius root k. There it is in the xy plane. Let's also intersect this with a vertical plane, vertical parallel to the xz plane, and see what we get. Such a plane has the equation y equals k. The surface, of course, has the equation z equals x squared plus y squared. So when you intersect those two, you'll get the equation z equals x squared plus k squared. This is the equation of a parabola. Draw it here in the xz plane. Its parabola shifted up by k squared. Finally, let's intersect it with a vertical plane in the other direction, so parallel to the yz plane. See what we get. Such a plane like that in purple has the equation x equals k. Intersect it with the surface z equals x squared plus y squared gives you the equation z equals k squared plus y squared. This again is a parabola. Draw it in the yz plane this time. Parabola opening up, shifted up by k squared. Intersecting surfaces with planes in various directions can be a really useful way of getting a picture of what's going on. Let's try a new example. Z equals x squared minus y squared. Start with the horizontal slices. You might also call these level curves. So we'll take z equals k and the surface, intersect the two to get the equation k equals x squared minus y squared. For k greater than 0, that gives a hyperbola in the xy plane with crossing the x-axis at plus or minus root k. Now if k is negative, strictly negative, you get a hyperbola in a different orientation. Now the hyperbola crosses the y-axis at plus or minus root k. Finally, if k is 0, you get these two intersecting lines, y equals x, y equals minus x, which is easy to see if you factor this equation, setting k equals 0. Okay. Look at vertical slices, parallel to the xz plane this time. Y equals k, so we get the equation z equals x squared minus k squared. This is a parabola opening up because of the positive coefficient in front of x squared, but shifted down by k squared. There's shifted down a little tiny bit for a small k. There's shifted down a little bit more, drawn in the xz plane, of course. Finally, let's intersect, let's take vertical slices parallel to the yz plane. So now x is equal to k, intersect the surfaces, and you get z equals k squared minus y squared. This is a parabola opening down because of the negative in front of y squared, and it's shifted up by k squared. So here in the yz plane is such a parabola, opening down, shifted up. Let's try to piece all this together. This can be tricky, but we have horizontal slices and two kinds of vertical slices. So let's start by drawing our axes. We'll try to draw these horizontal slices. So here's hyperbolas for k positive, hyperbolas for k negative. Then we have some parabolas opening up, and we have some parabolas opening down. This is kind of a mess, but it's hard to see what's going on. If you try real hard, you might see this kind of thing going on. Let me try to draw a cleaner picture. Here's what this looks like. A saddle, opening up in some directions, opening down in others. We'll use maple here to draw a better picture. Now, After we see the basic picture, I'll also add in an option to look at the contours. So there's the saddle. Now we can add in style equals contour here to see these lines which give the horizontal slices for various values of z equal to k. Now, let's talk in a little bit more generality. In 3D space with coordinates x, y, z, a quadric surface is the graph of a quadratic equation in x, y, z. Such an equation looks like this. You'll have x squared, y squared, and z squared. You'll have xy, yz, and xz, and you'll also have xyz. These will be the different terms, and you can multiply them by coefficients, a, b, c, d, e, f, g, h, i, j, add them up to get 0. This is an implicit equation, so you don't have z equals a bunch of stuff. This is an implicit equation. Let's note here, equations of this form include planes. If a, b, c, d, e, and f are all 0, so just delete it there, you get an equation of a plane. Let's assume this isn't the case. We don't want to talk about planes, we want to talk about more interesting quadric surfaces. Okay, so an equation like that gives you a quadric surface. Imagine you have some surface. Imagine that it's off in the corner of the room. What you'd like to do if you want to study it is, bring it closer and sort of center it in front of you and orient it in a nice way. By translating and rotating, you can consider surfaces sort of centered at the origin and oriented along one of the axes. Such a quadric surface has an equation of one of the following two forms. So either ax squared plus by squared plus iz equals 0, or ax squared plus by squared plus cz squared plus j equals 0, assuming that it's not simply a plane. These are what you might call standard forms for the equations of quadric surfaces. Okay, let me talk about this in just a bit more detail. In that red boxed equation there, you have 10 coefficients. At least one of them's got to be non-zero. So imagine dividing both sides by the non-zero coefficient, leaving you with 9 coefficients, or 9 degrees of freedom. 9 numbers that you can sort of wiggle around to get different quadric surfaces. These 9 degrees of freedom can be thought of as translating along the xyz axes, rotating about the xyz axes, or expanding along the xyz axes. Let's use up the 6 degrees of freedom, translating and rotating, to bring that surface, center it at the origin, and orient it in a nice way. That'll leave us with 3 degrees of freedom left, and you can see, looking at those standard forms, 3 degrees of freedom, either ABI or ABCJ. That second one, again, you can divide by a non-zero coefficient to be left with 3 degrees of freedom. There are the standard forms. Let's copy them and look at them here. Now, if either A, B, or C is 0, then the corresponding variable, x, y, or z, doesn't enter into the equation. So it can be anything. Let's look at an example. Look at the second one where A is 0. Take B and C to be 1 and J to be minus 1. Rewrite that as y squared plus z squared equals 1. So, real basic here. The point yz lies on the curve. Just think of this as a curve in yz space for now. If y squared plus z squared equals 1, that gives the unit circle. Now, if you want to think of this as defining a surface, you'd say a point xyz lies on the surface if y squared plus z squared is 1. That's the only condition. X can be anything. So how would we graph it? Let's draw xyz space here. We'll draw the unit circle in the yz plane, and since x can be anything, you can just stretch that out along the x-axis to get a cylinder. You can have other types of cylinders as well. For example, the equation z equals x squared doesn't depend on y. So you could draw a parabola in the xz plane, then stretch that out along the y-axis. Y can be anything. This is what you'd call a parabolic cylinder. We use maple here just to see a slightly cleaner picture of it, just for fun. We'll plot it, and we'll just rotate it, and just have a look. There it is. So, the standard forms, there they are, of quadric surfaces include any conic section, either an ellipse, parabola, or a hyperbola, in any of the planes, like the xy plane, xz, or yz plane, and then stretch that particular conic section out along one of the axes. Like for the xy plane, it'd be the z-axis. For the xz plane, it'd be the y-axis. For the yz plane, it'd be the x-axis. So from those standard form equations, we can get any kind of cylinder of any kind of conic section. What other kind of surface can we get? That's what we'll see in the next video.